The entire concept of paging and the page table has been invented, proposed just to solve one problem, uh, to decrease the wastage of memory because of external fragmentation, right? So you know this. So the entire concept of external fragmentation is, since the process has to be contiguous, the rule that was introducing external fragmentation because of the holes that in the dynamic memory allocation, right? And now if the process can be present at any place, that can solve the external fragmentation. So in order to have that flexibility, that we can load the process anywhere by breaking it into pieces, we got paging into picture. Now the paging's main purpose is to save the memory or conserve the memory or decrease the external fragmentation or decrease the wastage of memory. But then paging has got its own overhead. So what is it? Page table. And the page table size could be very big. So see this example. Let us assume that virtual address space or the size of the process is 4 GB and the page size is assume that 4 KB. Then how many pages will be present? 1 million pages will be present, right? And for each for 1 million pages, if I have to represent one entry, that the page table itself is going to be very big. And now in order to run this process, before running that, you have to load the page table entirely, right? And now what is the problem with that? If I load the entire page table, that itself is going to eat up the memory which you are trying to solve, save it from the external fragmentation. Then there have been various efforts done in order to save the time, right? So in order to save the space. So in order to save this space, what people did is, instead of loading the entire page table into main memory, they are using the concept of locality of reference. Locality of reference says that over the lifetime of a process, at any particular instance of time, it will be referring to only small number of pages, right? So most of the references will be to a small number of pages at any point of time, but then the small number of pages might vary from time to time. That is locality of reference. So locality of reference says that in order to run a process, you need not run the entire, you need not load the entire process. You just load only few pages, and therefore you can even load only the page table entries which are concerning to those pages, right? And now that is called locality of reference, right? So now what I mean to say is, in order to save the space or stop the wastage of space from the page table, what people did is, they have used this multi-level paging. So using multi-level paging, they divided the page table into small parts, and they are loading only the part which is required at that particular moment. If it is not required now, we are not going to load it, right? So that concept is fine. But then it is again going to see, it is like this. I'll just tell you what I'm trying to say. See, there is external fragmentation. What is external fragmentation? Some of the memory is going to be wasted because of the holes in the memory, right? And now in order to solve it, compaction was one solution, and the other solution was, don't save the process contiguously, save it at different parts. That is fine. And now in order to solve this external fragmentation, paging was introduced, right? And now paging was initially thought to solve this external fragmentation, but later paging concept has introduced the page table. Now what is the problem with page table? The page table itself is becoming so big that it is going to take up that is going to eat up the space which you are trying to save from external fragmentation. Then in order to save this space, right, so it is going to take large space, right? Most of the cases large space. So how can I save this space, or how can I decrease the page table size? So one way to decrease the page table size is increase the page size, right? So I think you know this. If I increase the page size, if it increases, then what happens to page table size? Page table size decreases. How? If I increase the page size, the overall number of pages will decrease, and therefore the page table size will decrease, because page table size depends on number of pages into size of each page table entry, right? Therefore if I increase the page size, right, and now I can decrease the page table size, but then it is going to introduce one more problem. I told you, on average every process is going to waste half of the page size for internal fragmentation, right? See, initially external fragmentation was there. In order to solve it, paging was introduced. Because of paging we got page tables. Page tables were very large. Now in order to decrease the size of the page table, you might try to increase the size of the page, but if you increase the size of the page, right, then the number of pages will decrease, fine, and therefore page table size will decrease, fine, but that will introduce the internal fragmentation, right? So what happens if the page sizes are too big? It might actually become the same as static partitioning. If page sizes are too large, then they are called partitions, and entire process can go and sit in one partition, and again the internal fragmentation will come into picture. Or even if the entire process cannot fit in one page, what happens is, on average half of the page is going to be wasted by every process, right? Then what happens if the page size increases? Then the internal fragmentation is half of the page, right? Which means internal fragmentation will increase. So what is the solution then? Then the other solution is, we have used the page table is again divided into multi-level paging, right? So what is the advantage of multi-level paging? If I have various levels of paging, I'm not going to load the entire page table. I'm just going to load the page table which is required at that moment, which is very small, right? Fine. But then by using the multi-level page table, right, the overall time required is going to be increased. How? Watch it. Anyway, using page table, time is also going to be increased. So there is page table in the main memory, and then there is process in the main memory, right? Now whenever the CPU wants to get a word from the process, it has to first go into the page table and access the main memory once. Let us say main memory access time is m. It has to access it once, and then using that physical address conversion, which means, see, after I go to the page table, then only I can convert the virtual address to physical address. Now I can take the physical address and then I can go to the process and again access the required concerned word. Therefore one more memory access time is required. Without page table, earlier only one memory access time was required. Now because of the page table, I require two memory accesses, right? Which means effective memory access time is going to be 2 into memory access time. What is small m? The time taken to read a word from the main memory. Got it? And now anyway it is going to be increased because of the paging. If there is no page table at all, then this would just be small m, right? And now by using multi-level page table, we are even making the situation worse. How? If by using multi-level page table, there will be outer page table, inner page table, like this we can have many levels, and finally process somewhere here, isn't it? Now if CPU has to access a word from the process, it has to go through various page tables. It has to go through this page table and again this page table and again this page table and then this one, right? So obviously if every access is going to take m time, so it is going to take the number of levels into m plus one more m, right? So anyway, this space, if you try to save this space by using multi-level paging, okay, how does multi-level paging save this space? Because even though we have these many levels of page tables, at every level I'll have only one page. Even though the page table is going to be very big, at every level, at any time, you need only one page. You need not load the entire page table. Got it? That is how you can save this space. But the problem is, the time is going to be increasing, right? So when you are trying to decrease the size of the page table, it is not very easy, right? Then what people thought is, if we don't want to have, they thought this initially. If you want to decrease the memory access time, see, time is the major concern rather than memory. Time is the major concern here, right? See, now in this, let us assume that we have only one level page table, and now there is a process. This is page table and this is the process, right? So now in this page table, what is happening is, we are going through two levels of access, or two memory accesses. Now what people thought is, in order to cut down these two memory accesses, why don't we load the entire page table into the registers? This is what they thought. But then the problem was the registers are very costly, that they might not have that much space to hold the entire page table. Yes, if you load the entire page table into registers, maybe accessing the process, or maybe program execution will become faster, because obviously we are cutting down the time in order to read something from the main memory. But the problem here is the registers are costly and the registers are smaller, and even if we assume that let us assume that page table size is very small and the page table can completely fit in register. But the problem with this is we have to load the entire page table into registers whenever we start a process or whenever we switch the context. Every context switching time has to set all the registers, and it is going to take a lot of time. So if I put the page table in the registers, it is going to take hell a lot of time for context switching. That is why what people did is they have loaded the page table at some point in the main memory, and then they have just loaded the base address of the page table in one register, right? So that is called as page table base. So by loading only one register, the context switching is going to be faster. What is context switching? Whenever you try to run a process, you have to do some groundwork, like you had to set up all the registers, and maybe you had to initialize some few variables and all, right? And now by using this only one register to load the base of the page table, context switching time will be lesser. So storing the page table inside the registers is never a solution. The reason is, one thing is page table is going to be very big and the number of registers are going to be very costly, and the second thing is the context switching time is going to be very high. Then what is the other solution remaining? So then people have finally invented a solution where we will not use main memory or we will not use registers. We will use some kind of memory which is faster compared to main memory but cheaper compared to registers. That is called as cache, right? So people thought that we will not load this page table into registers. We'll introduce one more kind of memory which is faster than main memory and cheaper than registers. That is called as cache, right? Cache memory. And now using cache, the advantage is we can store more memory, more elements compared to what we could store on registers, and it is cheaper compared to registers and faster compared to main memory. And this concept is also called as TLB, translation look aside buffer. Translation look aside buffer, right? So what is the advantage of translation look aside buffer is whenever we try to access any page table entry, we'll try to see if that page table entry is present. Okay, let me introduce it in a detailed manner. See, so I told you about the locality of reference. Locality of reference means generally pages, a process will access only few pages for a long time, and then these few pages will keep on changing, but at any point of time a process will not access a CPU, and a process doesn't need the entire all the pages to be available. It requires only few pages, right? Then the concept is, whenever you need any page, then that particular page table entry will be referred, and whenever any particular page table entry is referred for the first time, we are going to load that page table entry inside our TLB. So like this. Now if we have CPU, right, then I'll have TLB. TLB is also called as associative memory. So what is the specialty of associative memory is, every element of this memory will have something called as tag element. Okay, and now using this tag, if you present any item, or if you present any key means some value, if you present any key, right, to this associative memory, it can search the entire associative memory with the key, and it can produce it can say whether the key is present or not. and in case if this key matches with any of the tags, it will take out that entry and give it to you. It will take out that page number and give it to you. Okay, how does it work is this way. Let's watch it. Let us say this is TLB, right? How does it work is, now if there is page table, this is page table and this is process. Okay, now CPU is generating the logical address. Logical address has two parts. One is page number and other is page offset, right? And actually we should go into the page table and we should get the frame number corresponding to that particular page number. That is the concept, isn't it? But then CPU, before going to the page table, what it will try to do is, it will try to give this page number to all the tags present in the associative memory or TLB. Now if this page number matches with any of these tags, it will immediately give the frame number, and you need not go to the page table which is present in main memory. Got it? So how does it help? Since the TLB is faster compared to main memory, you can directly convert the virtual address to physical address here, and then you can go into the main memory and get that particular word, right? So it is going to be faster this way. I'll just take an example and I'll tell you. See this. So some important points to note here is, TLB is going to be very small size. I mean, it is bigger than registers but smaller than main memory. Therefore, TLB might not be able to hold the entire page table. It will just hold the frequently used page table entries, which means if an entry has been used recently, that entry will be present in the page table, this TLB. Therefore, whenever you try to load the page table entry for the first time, you might have to go to the main memory. But then from then on, if this entry is present in the TLB, then you need not go to the main memory at all. I'll just take an example and explain you. See this. Let us say this is CPU, and the TLB access times is denoted by small t, 20 nanoseconds, which means in order to access TLB and decide whether a page table entry is present in this or not, the time taken is 20 nanoseconds, right? And now assume that the time taken to access the main memory, right, which means the page table which is present in main memory, time taken to access it is main memory access time, let me call it as M, which is 100 nanoseconds. Therefore, accessing TLB is faster compared to accessing the main memory, right? And now, in case if the page which you are searching for is already present in the TLB, then you need not go to the page table to get it, right? You can directly get the frame number in just 20 nanoseconds, isn't it? And now after you get the frame number from this TLB, you can directly convert your virtual address to physical address and then get to the process which is present in the main memory, and then you can get the particular concerned word in 100 nanoseconds. So in case if you can find the entry inside the TLB, the time taken is just 120 nanoseconds, right? But what happens if you don't find the entry in the TLB? Then in order to know that the entry is not present in the TLB, again the time taken will be 20 nanoseconds. Let us say the entry which you are looking for is not present in TLB because TLB size is small compared to the page table, therefore all the entries will not be there, okay? Or recently a page has never been referred and therefore it is never brought into the TLB. Then what we do is, in that case, first we have to search whatever it is, we have to search TLB first. So in order to search the TLB, time taken is 20 nanoseconds, and then you decided that the concerned element is not present in TLB. Then what we should do is, we should go into the page table and then get it. So in order to go into the page table and get that particular page table entry, the time taken will be 100 nanoseconds, which is used to access the main memory. And after this time, then only we can convert the virtual address to physical address. And after converting the virtual address to physical address, now you exactly know where in the process you should get the word, right? For that the time taken will be 100 nanoseconds. Got it? So in case if your TLB contains the entry, then the time taken is just 120 nanoseconds. If the TLB doesn't contain the entry, then first you have to check it and then go here and go here, as well as parallelly what happens is you might have to even write down that new entry in one of the slots available here, which means if you have recently referred a page table entry which is not present in the TLB, it is not just enough that you get the entry from the page table in the main memory. You should even make sure that that new entry is recorded in the TLB, so that your future references, it will be helpful. Then what happens is, in case if there is a slot available, we are going to write that there. In case if there is no slot available, then what happens is the entire one of them has to be searched. Either we use some page replacement policies, or we use some random method, or we do something and we just replace one of the existing page table entries with the new one. Got it? So now whenever we find the required page table entry in the TLB, that is called as TLB hit. TLB hit means the entry which you are searching for is present in the TLB, that is called as TLB hit. Let us say the TLB hit rate is 80%. So what does it mean? 80% of the time you can find whatever you are looking for in the TLB, that is called as TLB hit. I am talking about TLB hit. TLB hit or any hit, it means that whatever you are looking for is present in this. 80% of the time, let us say it is whatever you are looking for is present in TLB. And what happens the 20% of the time? 20% of the time it will not be present. That one I call it as TLB miss. Right? Then what happens to the effective memory access time here? Effective memory access time is 80% of the time it is present here, therefore 80% of the time this one happens, plus 20% of the time it is not present here, therefore I will put 0.2 here. Right? It is not present, then it is going to take this much time. Then what is the total time? I think if you compute it, it will come down to around, I think, 120 nanoseconds. Right? You please do it. You please do the math, or if you want me to do it, I will do it for you. Okay, you please do the math. So it is going to be 120 nanoseconds or 140 nanoseconds. I am not sure. I think it is 140 nanoseconds. Okay, so you please check the math. So anyway, what I mean to say is, if I don't have the TLB concept at all, then I have to go through main memory 2 times in order to get any word. In that case, how much time will it take? 200 nanoseconds. But by using the TLB concept, I have actually reduced the time taken to access the memory, right? So on average, the time taken will be 140 nanoseconds, which is close to 100, which is not close to 200. In case if you increase the hit rate, which means if you see that almost all the references which you make to the page table are present in the TLB, then it will even come down to very less number. As you increase the hit rate, you can find out that the time taken to access the main the effective memory access time will get reduced. So what is the formula here? The formula is, let us say TLB hit rate is H and TLB miss rate is 1 minus H, or let us say TLB hit rate is P. Then in case if it is hit in the TLB, then how much time will it take for me to access a word from the process? The time taken will be, I have to access the TLB first. So let us say T is the access time, or the T is the comparison time for T, and then after that, once I access this TLB, then I have to get the watch it. So P plus T, which is nothing but the TLB access time, plus M. So what does it mean? So whenever there is a hit and hit probability is P, then the time taken will be, first you access the TLB and then you get the memory address and access the memory, plus in case if there is a miss, then 1 minus P into, if it is not present in the TLB, then we are supposed to take the entry from the process table, which is page table, which is present in the main memory, and then go to the main memory and get the word, right? So in this case, you have to check that it is not present first, and then you have to go to the this page table once, and then finally to the process and get it, right? So just be warned here, one thing is this entire concept is applicable when for a single level page table, and this can be extended even for multi-level page table. How? Whatever levels of page tables there are, if it is present in the TLB, the required page table entry, then you need not look at the page tables at all. You can directly go to the process and you can get that. That is one thing. And in case if there are various levels of page tables, then what happens is, if it is present in TLB, nothing will change. If it is not present in TLB, then you have to find out that it is not present in TLB, for which time taken is T, and then if there are two levels, then you have to go through two memory accesses to get to the actual entry of the page table, right? Therefore, if I put K here, right? So what is K? K is the number of levels in the page table. So in case if K equal to 1, it means that one level page table is used. In the exam, if they didn't mention anything about the page number of levels, then don't go for it. In case if they mention it like it is 2 level, 3 level, then you can put K equal to so and so number. Got it? So this is the formula you can use. So how does it work? See, I'll just take an example and I'll explain you. Initially, let us say the page number produced is 10, right? And initially there will be nothing in the page TLB, because let us say we have just started now and there is nothing, and the page number produced is 10, right? Then what happens? Then CPU will search in the entire tags and it will not be present, and then it gives up, and then it will go to the main memory and take the entry whose for the 10, and now it will go to the main memory and it will get the concerned word by converting this page number into frame number. That is all over. And also it will update this this part here. In one of the entries it will update it and will say that page number 10 is now present and its frame number is so and so. Therefore from next time it will be a hit, right? And then I am not actually discussing how much will be the time taken to update this. So actually the time taken to update this is negligible, and this could be done in parallel when we are actually trying to access the main memory, right? So I'm not going to see how much time is going to be taken to update this. I'm just assuming that time will be negligible. And many times what happens is main memory access time will be so big that this factor will become very small, and sometimes in the question they might neglect it. Anyway, you can have it and still do it, and you'll get a close answer to the some number to the solution. Okay, fine. So that is how it works. So the tags are used in order to note the page numbers, right? So there is one more thing. When there are many processes in the main memory, there will be many page tables in the main memory, right? Then whenever this TLB is containing some entry, it might mean that this particular entry might belong to any of the page tables of any of the process, isn't it? So just to avoid confusion, there are two strategies. One strategy is you might either use along with the page number, you can either use the process number, or you can make sure that whenever you start a process, you flush the entire TLB by deleting all the entries which were present for the previous earlier process, and you can say that entire TLB contains only this particular process addresses, right? So in case if you want to have inside the TLB many process entries, many page table entries of different process simultaneously, you even have to mention what is the process ID. If you don't want to do it, then flush it every time whenever a process is started. But flushing it every time and again loading it is going to take a lot of time. That is why people will generally use even the process number also. But let's not complicate things. The questions on this will be very simple. So only two things. Either if the required entry is present in the main memory or not, in case TLB or not. In case if it is present in the TLB, this will be the time. In case if it is not present in the TLB, then this is the time. All right, let's solve some questions and you will understand it.